Isomers in coordination chemistry are going to be the topic of this lesson. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also do DAT, OAT, and MCAT prep as well. I'll leave a link in the description below for where you can find those courses. Now, this lesson is part of my new general chemistry playlist, which is almost complete here. But for at least the next couple of weeks, I'll still be releasing several lessons a week. So if you'd like to be notified every time I post one, or when I get started on my next playlist, then subscribe to the channel, click the bell notification. Isomers in coordination chemistry. So there's a range of detail in which this could be covered in your class. And some, this might get towards the end of the semester and it might be left out altogether. And for some of you, they might just like pay it a little bit of lip service. And for others of you, you might get a fair amount of detail on here, and you're my target audience. I'm going to go into a fair amount of detail on these isomers. So it turns out for two structures to be isomers, they've got to have all the same atoms. That's the first part. And it turns out there are two major classes of isomers. There are structural isomers and there are stereoisomers. And you kind of got to know in principle what's the difference here. And so for structural isomers, we say they have a different bond connectivity. And in our complex ions, we're going to find out that means usually that we're going to have different atoms bonded directly to the central metal ion. So we're still going to have the same overall atoms in the entire coordination compound or complex ion, but which ones are actually bonded to the central metal ion will change. So we call that a different bond connectivity. Now, on the other hand, stereoisomers are going to have the same bond connectivity. What's going to be different is the three-dimensional arrangement of the atoms. So all the same atoms will be bonded to that central metal, but how they're distributed three-dimensionally around that central metal ion, that's what's actually going to be different. So those are two different classes. Different bond connectivity, or same bond connectivity but different three-dimensional arrangement. Now, there are two types of structural isomers. There are also two types of stereoisomers. The two types of structural isomers are going to be linkage isomers and then coordination sphere isomers. So two types of stereoisomers would be geometric isomers and then optical isomers. And we're going to take some time to talk about all four of these different classes and then how you can recognize either by a formula or by the structure which of these types of isomers you might actually have. Let's start with linkage isomers here, again, a type of structural isomer. So we're going to have a different bond connectivity here. And so with linkage isomers, these only apply to certain ligands, and these ligands are those that might be able to link to the central metal ion through more than one atom. So if you recall, the hallmark of one of these ligands that are acting as a Lewis base is they've got to have a lone pair of electrons. Well, it turns out that for thiocyanate, we kind of draw out its structure. Looks like this here, and it turns out because the sulfur has lone pairs and because the nitrogen has lone pairs, it turns out we've got an option here. It might be bonded through the central metal atom to the sulfur atom, in which case we see this here. Notice the bond is in every case to the sulfur, so we call that thiocyanate as a ligand. So on the other hand though, if nitrogen's got a lone pair, and if it's bonded through the nitrogen as we see here, so we call that isothiocyanate instead. But notice it's all the same atoms, but which ones are directly bonded to the central metal ion is what's different. Here the iron is bonded to all the sulfur atoms. Here the iron is bonded to all the nitrogen atoms instead. There's only a handful of ligands you might have to worry about this. And the other one you might see is cyanide here. And again, because the two atoms on either end both have a lone pair of electrons, you got two options here. And we've got cyano if it's bonded to the carbon, or isocyano if it's bonded through the nitrogen. So same kind of thing here. It is named differently depending on which one. And when they put it in the formula, they will actually write it in the order in which it's bonded. So here it's bonded through the sulfur, so they wrote the sulfur first. Over here it's bonded through the nitrogen, so the nitrogen's written first in the formula when identifying the ligand. So those are linkage isomers. So the next type of structural isomer is going to be the coordination sphere isomer. Let's get a couple of those on the board. So the next type of structural isomer is what we're going to call coordination sphere isomers, and it turns out these come in two varieties as well. And what's really going to be different about these coordination sphere isomers is what's in the coordination sphere, so the ligands and the central metal ion. And then what's out of the coordination sphere, which is usually we think of as ions, but it turns out we can also have what are called hydrates, water molecules that are kind of held within the crystal structure in different places, but they're outside the coordination sphere. So first off, we'll start with ionization isomers, and this is just going to be a difference of which ions are acting as ligands in the coordination sphere and which ones are just counter ions outside the coordination sphere. And so in this first example, we can see we've got 4 water ligands, 4 aqua ligands, and then 1 bromo, 1 chloro ligand, and then a chloride counter ion. But in the next one, what you'll find out is that this chloride and the bromo are going to trade places so that we end up with two chloroligands instead of just one, and then the bromide ends up as the counter ion instead. And so which ions are inside and outside the coordination sphere, which ones are acting as ligands versus which ones are acting as the counter ions, that's what's going to be the difference in these ionization isomers. And again, what atoms are directly bonded to that central metal ion are indeed different. So again, this is a type of structural isomer. So, and it's not that the same ligands are bonded as part of the coordination sphere like we saw in linkage isomers, just with different atoms being bonded. But here we have what's actually bonded to the central metal ion as far as the ligands goes is different. And then what's outside the coordination sphere. And they're just trading places. So the other type we're going to have, the other type of coordination sphere isomer is going to be what's called a hydration isomer. So when you have hydrates, and so there are certain molecules that just happen to absorb water, and oftentimes we put little packets of silica gel and stuff like that in your luggage or in new clothes or things of this sort because it absorbs water. They're hygroscopic, we say. So it turns out some of these coordination compounds are also potentially hygroscopic, and they might absorb water. And we can't really put it on the structure here in any identifiable way because it's really going to be put in different places within the entire crystal structure of a coordination compound. So, but the way we represent it was if we put a dot H2O, and it might be one water, it might be two waters, it might be seven waters, just some variable number of waters associated with the structure. And so in this first example, we see we've got 4 aqua ligands and 2 chloroligands in the coordination sphere bonded to chromium. Then 1 chloride counterion and 1 water that is part of a hydrate here, but again, still not part of the still not part of the coordination sphere. But in the second example, now we've got 5 waters, 1 chloroligand, and then 2 chloro counterions. And so effectively what's happened is that one of the chloroligands has traded places with the water here to get this second one here. And so we do have a different bond connectivity, that's structural isomers. What's in and outside the coordination sphere is different, so they're coordination sphere isomers. And then it's actually waters that are being traded inside and outside the coordination sphere, so we'll call them hydration isomers. And so now we've covered all of the structural isomers, and students don't usually struggle as much with these as they do with the stereoisomers, which we're going to devote some time to talk about now. All right, so let's talk about geometric isomers. This is our first of 2 types of stereoisomers. And again, a stereoisomer, just recall, that has the same bond connectivity, but a different 3-dimensional arrangement of the atoms. And geometric isomers can also be called cis-trans isomers. And this different 3-dimensional arrangement really just comes down to when 2 groups are either 90 degrees apart or 180 degrees apart. And when they're 90 degrees apart, we call it cis. And when they're 180 degrees apart, we call it trans. So that's going to be kind of the deal here. And it turns out there's 2 different geometries where this is possible. So with a coordination number of 4, it's possible in square planar complexes because 2 groups can either be 90 degrees apart like they are here or 180 degrees apart like they are here. Now, before I can ask you to recognize that these are 90 versus 180, there's a little tool here we're using when drawing these 3-dimensional structures on, well, I guess these technically are planar, but we're trying to draw them with some perspective coming off the whiteboard here. And the idea is that we call these wedged bonds, these darker ones right here. And when you use a wedged bond, it means it's coming out of the board. So this bromine would actually be out in front of the board here, and this chlorine out in front of the board over here as well. And then we refer to these as dashed bonds, and they mean they're actually going into the board away from you. So, and again, this is just a way of representing some 3-dimensional perspective. And so in this case, these 2 chlorines again are 90 degrees apart. So, but in the next one, these would be exactly 180 degrees apart. This chlorine would be coming out of the board and off to the right. This one would be going into the board and off to the left, and they'd be 180 degrees apart. And so when they're 90 degrees apart, we call it cis, and when they're 180 degrees apart, we call it trans. Now you've got to be a little careful when you've got a coordination number of 4. So, and it turns out only certain metals like platinum can even have a coordination number of 4, or at least commonly will have a coordination number of 4. But you got to also remember that there's 2 geometries possible, square planar and tetrahedral. Had these been tetrahedral, well, in a tetrahedral structure, all the bond angles are 109.5. There's no like 90 versus 180. It's just all 109.5. And so in a tetrahedral geometry, cis and trans isomers, geometric isomers, are not even possible. So, but in a square planar geometry, they totally are. But the key is you got to have exactly 2 of the same ligand, not 3, not whatever. So, and it's just 2 of the same ligand. Well, here I had 2 chlorines and 2 bromines, but the truth is I only had to have 2 of just one of them. Like, let's say I take one of these bromines and replace it with an iodine, both here and say here. Well, I'd still have a relationship between these chlorines being either 90 degrees apart or 180 degrees apart. And so the key is, this is one example of a way of getting exactly 2 of a ligand being 90 or 180, but it's not the only way. All right, the other ways we're going to see this is two examples in octahedral structures. And in an octahedral structure, any two adjacent ligands are 90 degrees apart. So like these two are 90 degrees apart, these two are 90 degrees apart, these two are 90 degrees apart, these two are 90 degrees apart. But you also then have the ones that are exactly on opposite sides that are 180 apart. So like these two are 180 apart, these two are 180 degrees apart, and then these two are 180 degrees apart. And so as a result, you now have this possibility again of having cis and trans. And so if you have exactly two of the same ligand again in an octahedral complex, they might end up 90 degrees apart in adjacent positions like this one, in which case we'd call it the cis isomer. Or they might end up 180 degrees apart, like in this example, in which case we'd call it the trans isomer. And notice in naming it, we just slap the phrase cis or trans, the prefix, right on the front of the formula, and we put it right on the front of the name, it turns out, as well. All right, we got one more here, and let me get that up on the board. Okay, so the last place these geometric isomers are going to show up here is in this case, we've got two bidentate ligands and then two monodentate ligands. Those two monodentate ligands can be the same, they can be different. And technically, I could have just had four monodentate ligands instead of these two bidentate, but this is probably the more common way it shows up. But the key is that the last two ligands you have, whether they're same or different, you have the option. They could be 90 degrees apart, like here, in which case that would be the cis version, cis isomer, or they could be 180 degrees apart, as is the case here, and that's the trans version. So that's kind of the deal. And these are your three places, three most common places by far, where you're going to find these geometric isomers. Again, either in a square planar complex with exactly two of the same ligand, or in one of these different variants of these octahedral complexes. Let's take a look at optical isomers. So now we'll finally talk about optical isomers, and these are the trickiest of the different isomers we'll talk about. And when I spoke in the last lesson about drinking some coffee before getting to this lesson, this is the reason why. It's all about these optical isomers. So as a reminder, optical isomers are a type of stereoisomer, so they have the same bond connectivity, but a different three-dimensional arrangement. And it turns out the reason they're called optical isomers is because these types of compounds will actually rotate plane polarized light. And you're like, oh yeah, that makes perfect sense to me, Chad. No, you're like, well, what in the world is plane polarized light? So we gotta talk about that. Well, it turns out light has wave-like properties, and it can have like a vertical orientation or a horizontal orientation or a diagonal orientation or anything in between. And so we would call that unpolarized light when it's just kind of got all these different orientations. But if you shine it through a polarizing filter, that polarizing filter, and this is kind of the principle in which polarizing sunglasses work on. So when you shine it through that polarizing filter, all the different orientations, but largely one are blocked. So let's just say we have a polarizing filter that blocks out everything except the vertically oriented light. Okay, so that's plane polarized light. Well, it turns out if you shine that plane polarized light through a solution of most compounds, it just comes out vertical still on the other side. It hasn't been rotated in any way, shape, or form. However, if you shine it through a solution of something that is optically active, so which turns out these optical isomers, each of them individually is what we call optically active, the light's not going to come out vertical anymore. It's going to get rotated one way or another. And these different optical isomers, it turns out they rotate light by exactly the same amount, but in opposite directions. Kind of a weird thing. So, but in some way, shape, or form, so this plane polarized light actually interacts with these lovely optical isomers. So it turns out these compounds that have optical isomers get the adjective chiral. So chiral compounds rotate light and they have optical isomers. So whereas achiral compounds don't rotate light and they don't have optical isomers. So all the compounds we're talking about in this section are going to be chiral molecules. And the way you recognize a molecule that is chiral, and this is going to be a little bit strange, is that you have a molecule and it's perfect mirror image and they're not identical. And the word we use is nonsuperimposable. So when you have nonsuperimposable mirror images, those are optical isomers. And it turns out individually they're going to rotate light, as we'll see here in a minute. So but if you take a look here, these are perfect mirror images just reflected right across a mirror plane here. So, and you might be like, wait a minute, Chad, that doesn't look like mirror images. So, but they are. Notice the iodine here's on the left, on the right, here it's on the left, here the bromine's on the left, and here the bromine's on the right. But again, don't forget what these wedged bonds and dashed bonds mean. So it turns out that our wedged bonds and dashed bonds there, so the chlorine's not on the left of the fluorine. It's actually the chlorine's right in front of the fluorine. So the chlorine's coming out of the plane with a wedged bond, the fluorine's going back into the plane with a dashed bond. And so if you look at it sideways, you got one in the front, one in the back, and the one in the front is directly in front of the one in the back, but I can't draw it like that. It put the wedge right on top of the dash and the chlorine right on top of the fluorine. It would just look nonsensical. And so we just offset them a little bit, but that's what it means. And so when it's reflected, well, the chlorine is out here, and it's still going to be out here on the reflection. And the fluorine's in the back, and it's still going to be in the back on the reflection. And whether you write them on the left and the right is irrelevant because they're not on the left or the right. They're right in front and behind each other. All right. So these are identical these are perfect mirror images of each other, but they're not identical. They're non-superimposable. Notice if you wanted to superimpose these, you know, if you want to get this bromine right where this bromine is and this iodine right where this iodine is, you want to flip the whole thing over. But if you flip the whole thing over, well, that chlorine that is now pointing out at you, flip it over, would be pointing away, and it would be a dash bond, not a wedge bond still. Same thing with the fluorine. It's a dash bond, and it's going away from us right now. So, and once again, if we flip this whole thing over, well, then it would be pointing out of the board and would be a wedge bond, not a dash bond. So these are not the same structure. They're mirror images, but they're not the same. And when you have that being the case, we call these chiral. And it turns out we refer to the relationship between these two molecules. We refer to them as being enantiomers of each other. Very funky word there. So chiral compounds have enantiomers, achiral compounds don't have enantiomers. Chiral compounds are optically active and have optical isomers, and these optical isomers, we refer to them as being enantiomers of each other. So there's some vocab words we had to learn here. It turns out that either one of these compounds, one's going to rotate light one direction, one's going to rotate light to the other direction, so by the same amount. And we can't predict it by looking at it. Yes, you have to put them in what's called a polarimeter and just see which way they rotate light. And it turns out we actually name them off quite often differently based on which way they rotate light. We talk about one rotating it in the positive direction, one rotating it in the negative direction, and so you might have the plus isomer versus the minus isomer. So oddly enough. Now, it turns out for coordination number 4, these optical isomers are possible for tetrahedral complexes, but not for square planar. But it turns out that they only occur in these tetrahedral complexes when the central metal ion is bonded to 4 different ligands. All 4 have to be different. So if any 2 of these are the same, there's no optical activity. So, and it turns out what you'd find out is that when any 2 of these end up being the same on a tetrahedral structure, the result is that the molecule in its mirror image would end up being superimposable, absolutely identical if you rotate them around. Oh, the last thing I did want to say here is that if these rotate light in opposite directions, well, it turns out if you mix these 2 together in solution and you have an exactly 50-50 mixture, it gets a special name. We call it a racemic mixture. So, and it turns out if, half the molecules in your solution, or half the ions in this case in your solution, want to rotate light one direction, and half of them want to rotate light in the other direction, well, then this light passes through the entire solution. It should, on average, encounter the same number of each type of molecule, and as a result, not be rotated in any net fashion. And so it turns out these racemic mixtures, which is a 50-50 mixture of the 2 different enantiomers, that mixture ends up being optically inactive. It doesn't rotate the light. So either one of these separate rotates light. But 50-50 mixture, it has to be exactly 50-50. You can't have an excess of one over the other. So, but that exact 50-50 mixture is a racemic mixture. It is optically inactive. All right, if you get to taking organic chemistry in the future, you'll find out that there are oftentimes you'll have carbon being at the center of a tetrahedral structure, and quite commonly you'll visit this kind of chiral structure with enantiomers and racemic mixtures. All this vocabulary is something you will visit again. So, but there's 2 examples in octahedral complexes we got to talk about, and you won't see these 2 in organic chemistry at all. So, but the same rules will still apply. We'll still talk about optical isomers and enantiomers and chiral. So, however, recognizing when these are possible is going to be a little bit trickier. So the second example of an optical isomer here is going to be when you've got 3 bidentate ligands in an octahedral complex here. And so here I've got Fe, ethylene diamine 3 here, so FeN3, 2+, and octahedral 3 bidentate ligands. And if you take the exact mirror image, and you can see that these are mirror images of each other, it turns out these are not superimposable. And I'm having to tell you this because looking at this and remembering what wedges mean and what dashes mean, if you can magically see this, it must mean like you are a crazy artist or something who can see three-dimensional things. And so I've drawn this and I've taken the time to draw it, but I don't actually expect most of you to see this. I struggle to see this. So, but if you built a three-dimensional model of this structure, you'd find out that there are two mirror image versions of this that are not identical. They're non-superimposable. And so these are optical isomers, and this is the second case where you should recognize it from a formula when you've got exactly 3 bidentate ligands on an octahedral complex. So I drew it for you again, but most likely you're going to recognize it from a formula just because you've memorized when these optical isomers can exist. But these are mirror images. They're non-superimposable. We could describe either one of these as being chiral. They're optically active. These are enantiomers of each other. And if you mix them in a 50-50 mixture, that would be a racemic mixture. All right, so the last example we're going to encounter optical isomers here. It's once again going to come in an octahedral complex when you have exactly 2 of a bidentate ligand and 2 of a monodentate ligand. If we take a look at these two, so they're perfect mirror images of each other. Here I've got the 2 chlorines on the wedge and dash on the left. Here they're on the wedge and dash positions on the right. They are mirror images of each other. But if you flipped this guy over to make them match up, the chlorines would indeed match up in that sense, but you'd find out that your ethylene diamines would not match up. So if you flip this over 180 degrees, well, this dash then is going to end up with a wedge, and you'd find out that the top one would actually be connected right here with OFN between these two, and then between these two instead. And so these perfect mirror images are not identical. And once again, this is difficult to see, especially from a 2-dimensional drawing. And if you built a 3-dimensional model, you could see it. So, however, what a best way to kind of to approach this is just pure memorization again. So, and again, these 2 chlorines had to be 90 degrees apart as well. They had to be cis. So octahedral complex, cis, 2 bidentates, 2 monodentates, that's going to have optical isomers. The 2 mirror images are going to be different from each other, not identical, non-superimposable. They are enantiomers. This guy's chiral, this guy's chiral, this guy's optical active, this guy's optical active, and relative to each other, we can call them enantiomers or we can call them optical isomers. I just want to point out the trans version here. This guy is not chiral. This guy is not optically active. He does not have an enantiomer. He does not have an optical isomer. If you were to draw the perfect mirror image of this guy, it would look exactly like this. Notice, just try and reflect it. Well, if you do a perfect reflection, the chlorine would still point up, this one would still point down, and these would look exactly like this. It would look exactly the same because it's perfectly superimposable, perfectly identical. And so the trans version of this does not have optical isomers. So, but notice we can get tricky here. So if I said, how are these 2 related? You should say optical isomers or enantiomers. But notice I could say, well, how are these 2 related? Well, these 2 are isomers as well. They're cis and trans isomers. That is geometric isomers, a type of stereoisomer. But again, they're not optical isomers. If I said, how are these 2 related? Same thing. Again, these are cis-trans isomers. And again, they're going to be geometric isomer, type of stereoisomers, but they're not going to be optical isomers. So lots of different possible relationships now of all these different isomers. And again, it is usually the stereoisomers that give students a little more fits. And again, seeing the 3-dimensionality is the biggest pain in the butt. So know some definitions. So, and then as far as the stereoisomers go, know kind of based on how the formula looks, based on what I've listed here with examples on the board of what I've put on the study guide here, but no, based on looking at a formula, should that be capable of optical isomers or geometric isomers, something like this? And in this case, with that exactly 2 of a ligand in an octahedral complex, you should be like, oh yeah, that's going to be capable of cis and trans isomerism, geometrical isomerism. But then also look and say, oh, 2 bidentates, 2 monodentates. Chad taught me that that's also going to be capable of optical isomerism as well. Now, if you found this lesson helpful, a like and a comment, let me know, are pretty much the best things you can do to support the channel. Now, I've stated that my goal here is to take the stress out of learning science, but my secret goal is also meant that when you say you're such a Chad, that you mean something other than what you currently would mean when you say that. I just want to remind you about my General Chemistry Master course that includes final exam rapid reviews, practice final exams in case you're studying for finals, and also if you've got a preference on what I do for my next playlist, biochem, redoing physics, or biology are all in the running. Let me know in the comment section below for that as well. Happy studying.